To ensure safety around in-ground pools, equipotential bonding is essential, especially when dealing with below-surface lighting. This process aims to minimize voltage differences in and around the pool area, preventing electric shock hazards. Here's the most accurate procedure for assessing equipotential conditions, followed by acceptable resistance limits. Firstly, disconnect all electrical equipment associated with the pool. This includes the pump, filter, lighting, and any other electrical devices connected to the pool's electrical circuit. This step ensures that any voltage readings you obtain are not influenced by active electrical sources. Secondly, fill the pool with water to its normal operating level. Water is a conductor, and filling the pool allows you to accurately measure voltage gradients within the pool environment. Thirdly, submerge a reference electrode into the pool water. A copper sulfate electrode is commonly used for this purpose. The reference electrode provides a stable and known electrical potential against which other measurements can be compared. Fourthly, connect a voltmeter between the reference electrode and various points in and around the pool. These points should include all conductive surfaces, metal attachments, and lighting fixtures. Examples of conductive surfaces include the pool walls, coping, and steps. Metal attachments include ladders, diving boards, and handrails. Lighting fixtures and their associated wiring should also be tested. Fifthly, record the voltage readings obtained between the reference electrode and each test point. These readings will indicate potential difference between each point and the reference electrode. Accurate recording is crucial for later analysis. According to ANSI/APS-P-11 standards, the maximum permissible voltage at any point in a pool environment relative to the reference electrode is 5 mV for alternating current voltage and 10 mV for direct current voltage. These limits are designed to minimize the risk of electric shock. To calculate the corresponding Ohm's limits for acceptable voltage drops, we can use Ohm's law. Ohm's law states that voltage in volts equals current in amps times resistance in ohms. This can be written as volts equals amps times ohms. Rearranging this formula to solve for resistance, we get resistance in ohms equals voltage in volts divided by current in amps. To apply this to our equipotential bonding assessment, we use millivolts and milliamps. Assuming a conservative maximum current leakage of 1 milliamp, we can calculate the acceptable ohms limits. For alternating current voltage, the calculation is 5 mV divided by 1 milliamp, which equals 5000 ohms. For direct current voltage, the calculation is 10 mV divided by 1 milliamp, which equals 10,000 ohms. Therefore, the acceptable ohms limits are 5000 ohms for alternating current and 10,000 ohms for direct current. There are a few additional notes to consider during this process. The procedure should be repeated at different times of the day and under different conditions. For example, measurements should be taken with the pump running and with swimmers in the pool to account for potential variations in electrical potential. If any voltage readings exceed the acceptable limits of 5 mV for alternating current or 10 mV for direct current, further investigation is required to identify and correct the source of the excessive potential difference. This might involve checking the bonding connections, inspecting the electrical equipment for faults, or consulting with a qualified electrician. The following provides a more detailed breakdown of the steps involved in performing this test, as well as a deeper dive into the calculations and the importance of each step. First, preparation is key. Before you begin any testing, ensure the pool area is safe. There should be no swimmers in the pool during the test, and access to the pool area should be restricted to prevent accidental entry. Gather all necessary equipment, including a calibrated voltmeter with millivolt sensitivity, a reference electrode, copper sulfate is recommended, connecting leads, and a recording sheet to document your measurements. Verify that the voltmeter is functioning correctly and that the reference electrode is in good condition. Next, disconnect all electrical equipment. As mentioned earlier, disconnect all electrical equipment from the pool's electrical circuit at the source, typically the circuit breaker panel. This prevents any unintentional current from influencing your voltage readings. Clearly label the disconnected circuits to prevent accidental re-energizing during the testing process. Then fill the pool. Fill the pool with water to its normal operating level. Ensure that the water is free from any debris that could interfere with the electrical conductivity. Allow the water to settle for a few minutes before proceeding with the test to minimize any disturbances. After this, you will need to submerge the reference electrode. Submerge the copper sulfate reference electrode into the pool water, positioning it near the center of the pool. Ensure that the electrode is fully submerged and that the copper sulfate solution is properly hydrated according to the manufacturer's instructions. The reference electrode should be stable and not in direct contact with any conductive surfaces. Connect the voltmeter. Connect the voltmeter between the reference electrode and the various test points. Use separate insulated leads to connect the voltmeter to each point. Ensure that the connections are secure and free from corrosion. Start by testing the conductive surfaces of the pool, such as the pool walls, coping, and steps. Then test the metal attachments, including ladders, diving boards, and handrails. Finally, test the lighting fixtures and their associated wiring, including the metal housings and junction boxes. Now record the voltage readings. At each test point, record the voltage reading displayed on the voltmeter. Note whether the voltage is alternating current or direct current. Document the location of each test point and the corresponding voltage reading on your recording sheet. Take multiple readings at each point to ensure accuracy and consistency. If the readings fluctuate significantly, investigate the cause of the fluctuations before proceeding. After you have recorded all the readings, perform the calculations. Using Ohm's law, calculate the corresponding resistance values for each voltage reading. As a reminder, the formula is resistance in ohms equals voltage in volts divided by current in amps. Assuming a maximum current leakage of 1 mA, calculate the resistance for both alternating current and direct current voltage readings. Compare the calculated resistance values to the acceptable limits of 5,000 ohms for alternating current and 10,000 ohms for direct current. Now analyze the results. Analyze the recorded voltage and resistance values to determine if the equipotential bonding system is functioning correctly. If any voltage readings exceed the acceptable limits or if the calculated resistance values are below the acceptable limits, further investigation is required. Identify the specific test points where the limits are exceeded and prioritize those areas for further inspection. After you perform the analysis, determine the next steps. If any issues are identified during the analysis, take corrective action to address the problems. This may involve tightening bonding connections, replacing corroded components, or installing additional bonding conductors. Retest the equipotential bonding system after making any repairs or modifications to ensure that the issues have been resolved. Document all corrective actions taken and the results of the retesting. Remember additional considerations. Repeat the testing procedure at different times of the day and under different conditions to account for potential variations in electrical potential. Test the system with the pool pump running, with the pool lights on, and with swimmers in the pool to simulate real-world operating conditions. Pay close attention to any changes in voltage readings under different conditions. Also, maintain detailed records of all testing procedures, voltage readings, resistance calculations, and corrective actions taken. This documentation will be valuable for future reference and for demonstrating compliance with safety standards. Ensure that the testing is performed by a qualified electrician or pool professional who is familiar with equipotential bonding requirements and testing procedures. This ensures that the testing is performed correctly and that any issues are identified and addressed appropriately. The importance of equipotential bonding in swimming pools cannot be overstated. Equipotential bonding is a critical safety measure that helps to prevent electric shock hazards in and around swimming pools. By connecting all conductive surfaces and metal attachments to a common bonding grid, equipotential bonding minimizes voltage differences and reduces the risk of electric shock if a fault occurs. Regular testing and maintenance of the equipotential bonding system are essential to ensure its continued effectiveness. Ignoring equipotential bonding requirements can have serious consequences. Failure to properly bond and test a swimming pool can create a dangerous environment for swimmers and others in the pool area. Electric shock can result in serious injury or even death. In addition, failure to comply with equipotential bonding requirements may result in fines or other penalties. If you have any doubts about the safety of your swimming pool's electrical system, consult with a qualified electrician or pool professional. They can assess the system, identify any potential hazards, and recommend appropriate corrective actions. Taking the time to ensure that your swimming pool is properly bonded and tested is a small price to pay for the safety of your family and friends. The technical aspects of equipotential bonding rely on the principles of electrical safety and grounding. Grounding is the process of connecting electrical equipment to the earth, providing a low impedance path for fault current to flow back to the source. This helps to trip circuit breakers or fuses, disconnecting the power and preventing electrical shock hazards. Equipotential bonding takes this concept a step further by connecting all conductive surfaces and metal attachments in the pool area to a common bonding grid. This creates an electrically equipotential zone, where there are minimal voltage differences between different points. The purpose of equipotential bonding is to ensure that if a fault occurs, such as a wire shorting out, the voltage on all conductive surfaces will rise and fall together. This prevents a person from becoming a path for current to flow, which could result in electric shock. The bonding grid typically consists of a network of copper conductors that are connected to the pool's reinforcing steel, metal components, and electrical equipment. The size and spacing of the bonding conductors are determined by the electrical codes and standards. The bonding grid must be properly installed and maintained to ensure its effectiveness. This includes making sure that all connections are tight and free from corrosion. Regular inspections should be performed to check for any signs of damage or deterioration. In addition to the bonding grid, other safety measures may be required, such as ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect small amounts of current leakage and quickly disconnect the power, preventing electric shock. GFCIs are typically required for outlets and circuits near swimming pools. The selection of appropriate materials for the bonding grid is also important. Copper is commonly used because it is a good conductor of electricity and is resistant to corrosion. However, other materials may be used as long as they meet the requirements of the electrical codes and standards. The installation of the bonding grid should be performed by a qualified electrician who is familiar with the electrical codes and standards. The electrician should carefully follow the manufacturer's instructions and ensure that all connections are properly made. After the bonding grid is installed, it should be tested to verify its effectiveness. This can be done using a voltmeter and an ohmmeter. The voltmeter is used to measure the voltage between different points on the bonding grid. The ohmmeter is used to measure the resistance of the bonding connections. The voltage and resistance values should be within the acceptable limits specified by the electrical codes and standards. Regular maintenance of the bonding grid is essential to ensure its continued effectiveness. This includes inspecting the connections for corrosion, tightening any loose connections, and replacing any damaged conductors. The bonding grid should also be tested periodically to verify that it is still functioning correctly. The equipotential bonding requirements for swimming pools are complex and vary depending on the electrical codes and standards. It is important to consult with a qualified electrician or pool professional to ensure that your swimming pool is properly bonded and grounded. In addition to the technical aspects of equipotential bonding, there are also some practical considerations to keep in mind. For example, it is important to keep the pool area clean and free from debris. Debris can interfere with the electrical conductivity of the water and increase the risk of electric shock. It is also important to avoid using electrical appliances near the pool. Electrical appliances can introduce stray currents into the water and increase the risk of electric shock. If you must use electrical appliances near the pool, make sure they are properly grounded and protected by GFCIs. Finally, it is important to educate swimmers about the dangers of electricity and water. Swimmers should be instructed to avoid touching electrical equipment near the pool and to report any electrical hazards to the pool operator.